All right, so we're going to go ahead and get started. So I'm Neil, and I'm going to be leading this Intro to Machine Learning workshop. So thank you all for joining me today. So before I get started with the actual content of the workshop, I wanted to mention a couple of things. First off, this workshop is interactive, meaning that I'm going to be writing code, and you can write code along with me and run it on your local computer. So if you want to do this, you'll need to have Anaconda installed. So Anaconda is a set of data science packages for Python. So again, if you want to follow along and write code on your computer, you'll need to have Anaconda installed. Second, since I'm going to be sharing my screen, and since you'll probably want to be writing code on your computer, it would help to have either a dual monitor setup or a really wide monitor. Otherwise, it might be somewhat difficult to follow along. Now, if neither of those two things apply, that's perfectly fine. You can follow along with this workshop without writing any code, and I think you'll still get a lot out of it. Okay, and then one last thing. So this is an introductory workshop. So if you already know a lot about machine learning, I would recommend not answering the questions because some of these questions might be kind of trick questions or questions to kind of make you think about the content. So if you already know the answers, please don't answer. Let other people have a chance. Okay, so now to actually get into it, so I'm gonna go ahead and download the starter files we'll need for this workshop. So to do that, I'll just go to GitHub. So here I am at this intro ML21 repo right here. So we're gonna need these two files to get started. So to get these two files, we can just go ahead and do a git clone. So let's see if I can send this out in the chat. Okay, I don't think I can send it out in the chat. That's okay. So to get to this directory, or excuse me, to get to this repo, you can just go ahead and go to github.com/Neil-ash. So if you go ahead and do that, github.com Neil Neil-ash. So if you go ahead and do that, it'll take you to my GitHub page, and we've got this intro ML21, this guy right here. So you could go ahead and click on it. So intro ML2021. So this is the repo you're going to want on your computer in order to follow along with the code. So to do that, we can go ahead and take the link up top, and we can open a terminal, or if you're on Windows, a command prompt. And so we can navigate to the directory we want to be at. So here, I'm just going to go to my desktop. And now I'm going to pull these files. So I'm just going to go ahead and do git clone, and then copy and paste this URL up top. So, all right, git clone, and then the URL. Then I'm going to go ahead, hit enter. And so, okay, awesome. It's going to clone into here. And so, okay, awesome. So now I've got this directory on my computer. All right, so if you don't have Git set up, or if you don't know how to use Git, there's another way to do it, which is pretty simple, where you can just click on each of these files and then click on raw, and now right click and go to save as. Actually, we've got something in the chat. Just one second. Okay, someone just joined. What did they miss? All right, so a couple things. So I'm going to be writing code in this workshop, and you'll need Anaconda to follow along with the code on your local machine. So that's the first thing. And second, it'll be easier to follow along if you have dual monitors or a really wide monitor. If not, that's totally fine. You can just follow along with the workshop without writing code of your own. And so what I'm doing right now is I'm getting the starter files to follow along. So to get these starter files, you can just go to github.com/neil-ash. Actually, I will copy and paste this into the chat. Just give me a second. So chat. All right, so I sent out the URL in the chat. And so then you can go ahead and just git clone this URL, or you can go to these files individually, just click on them, click on raw, and then right click, and you can go save as, and then you can just save these files. But if you choose to do it this way, make sure you don't have the .txt extension, and make sure you save it as all files. All right, so we got a couple more in the chat. Okay, only send it to panelists, not attendees. Okay, yeah, thank you, Catherine. Thanks for getting that. I'll change that to panelists and attendees for next time. All right, I appreciate that, Cash. Okay, yeah. So you can go ahead, save this file, and then go back to this intro to ML, and then go ahead and save this guy too. And so again, this is only if you don't want to git clone it. And here, this comma separated values, that's fine too. Also, if any of you have any other questions, if I'm going too fast or too slow, feel free to stop me. Yeah, feel free to put stuff out either in the chat or in the Q&A. Okay, cool. So once you've got those two files downloaded, so here I git clone them onto my desktop. Now we're going to go and actually use some of the Anaconda packages that you should have downloaded. So to open Anaconda, I'm going to go ahead and search. And so to search, I'm just going to search Anaconda Navigator. And so Anaconda Navigator, so I'm going to go ahead and open that. So I've mentioned that you need Anaconda to follow along with this workshop. But what actually is Anaconda, right? So Anaconda is a set of data science packages for Python. So these are packages that you can import into Python. And Anaconda also comes with a bunch of IDEs where you can write code. So the one we're going to be using today is called Jupyter Notebook. So once you've got Anaconda Notebook, or excuse me, once you've got Anaconda Navigator open, you can go ahead and hit launch. And so when you hit launch, for me, it's going to open another terminal, and then it's going to show me all of the files on my computer. So next, we're just going to want to navigate to the directory where we cloned this repo just now. Okay, so desktop, and then, okay, where is it? Intro ML 2021. Okay, cool. So here it is, intro ML 21. So I'll give you a second to do that. So again, what it was just searching for Anaconda Navigator, launching Jupyter Notebook, and then just navigating to the directory where we had these two files saved. Again, if I'm going too fast or too slow, feel free to stop me and just let me know. All right, cool. So once we've got that set up, oh, we got something in the chat. Anaconda is still installing, unfortunately. Okay, if it's taking a long time to install, that's totally fine. You could just follow along with the with this screen shared here. Also, I'm gonna post the completed code at the end, so if you don't get everything down, that's totally fine. That's in chat. I clicked on Jupyter Notebook, and it says it's launching. Okay, yeah, it might just take a second to launch. It doesn't pop up. All right, it should open in a browser. I'm not sure how. Yeah, I'm not sure what the issue is with that. Okay, so it's gonna follow along. All right, so ML Workshop IPYNB. So this is what you're gonna want to click on. So when you open it, it should look something like this. Okay, so I've told you need Anaconda, you need to open Jupyter Notebook. But what is Anaconda? All right, I mentioned what Anaconda is, but I haven't mentioned what Jupyter Notebook is. So if you look at this file right here, you'll probably notice a few things about it. First, you can see there's some Python code, but there's also some plain text, or specifically Markdown. And another thing to note is that this code, it's segmented. It's separated into cells. It's not just one big .py file. So what's the deal with that? Well, this is the main thing about Anaconda. The main reason you might want to use Anaconda is because it separates code into cells, which means that you can run a Python file one cell at a time. And so this is really useful for data science projects where you might have a really big data set and you might want to bring that data set into your notebook once and then make changes to the data later on without having to re-import that data set every time you want to make a small change later on. So that's why Jupyter Notebook's really useful. It's also really useful for presentations like this, where you can see the output of the code just by running code line by line. All right, so that's a little overview of Jupyter Notebook. Next, I'll talk about how to actually use it. So in Jupyter Notebook, there are two modes. Well, actually, I should say one more thing about Jupyter Notebook, and that's why is it called Jupyter Notebook, right? That's kind of a weird name. All right, one other thing in the chat. Check a few pop-ups. Okay, thanks, Catherine. Okay, yeah, so why is it called Jupyter Notebook? So it's got kind of a weird name. So I'm gonna go ahead, toggle the header. So Jupyter, Anything you notice about the spelling of Jupyter here, specifically, why is there a Y instead of an I after the P? Any ideas with this? Oh, someone mentioned Python. Yeah, exactly. So it's called Jupyter Notebook because it supports 3 languages, Julia, Python, and R. So that's why it's called Jupyter Notebook. Actually, here we can see we have this IPYNB extension. So that stands for Interactive Python Notebook, because that's what a Jupyter Notebook is. It's interactive. Like I mentioned, you can run code code one cell at a time. All right, next, how to actually use Jupyter Notebook. So I'm going to toggle the header here. Okay, so the first thing to know is there are 2 modes. There's an overview mode and there's an edit mode. And you can tell what mode you're in based on the color of this bar right here. So right now we're in the overview mode and the bar is blue. So you can use the arrow keys to navigate around the notebook. And once you're in a cell, you can hit enter and it'll turn green, which means that you can actually start editing this cell right here. You can actually start writing some code. So this is the edit mode, and to go back to the overview mode, hit escape or just click out anywhere over here. Those are the 2 modes, how to go back and forth between them. Next, you can run these cells because this is code. So you can just hit run up top, or another thing you can do is you can hit command return. And so that's what I like to do. It's command return on Mac. It might be control return on Windows. Yeah, so that's how you navigate through Jupyter. That's how you run cells. And something else to notice is when I ran this first cell, you could see that the brackets went from empty to 1, which means that this is the first cell to have been run. And same with this, the brackets went from empty to 2. This is the second cell to have been run. And you can also run cells multiple times, which in this case doesn't do anything. So I guess this is the one thing that you should be careful of when using Jupyter Notebook, is that if you run cells out of order, you can run into some issues. And so if that ever happens to you, you can just go up to kernel and go restart and run all, or restart and clear notebook, and that should fix things for you. All right, we got another question in the chat. My Jupyter doesn't launch either. Huh, that's strange. Okay, so if your Jupyter doesn't launch, another thing you could do is you could just go to terminal and just type Jupyter Notebook and see if that works. Just in terminal, just type Jupyter Notebook. That's surprising to me that it's not allowing it to open. Yeah, it might be an issue with pop-ups. Yeah, so again, if it's not launching for you through the Anaconda Navigator, you can just go into your terminal and just type Jupyter Notebook, and that might work. Okay, so that's a little bit about Jupyter. Now I'm going to get into what we're actually going to be doing in this workshop. So in this workshop, we're going to be looking at a few machine learning algorithms and how they work. So to kind of motivate this, we've got a very simple data set. So we've got this data set of exam scores and university admittance. So this isn't real data, this is just synthetic data to kind of illustrate some concepts we're going to be talking about. So let's say there's some fictional university and you have to take 2 exams in order to get admitted into this university. So here we have student exam scores and student admittance for past students. So 0 means a student was not admitted, and 1 means a student was admitted. So if we look at the first student at index 0 here, we can see they got a 34 on the first exam, 78 on the second, and they were not admitted. And so that makes sense. 34 is a pretty poor score on the first exam. And if we look at this 5th student at index 4 here, we see they got a 79 on the first exam, 75 on the second exam, and they were admitted. So this makes sense. They did decently well on both exams. Okay, so here we've got this historical data, and we're going to use this historical data to predict admittance for future students. So again, this is a very simple data set, and it's going to be used for illustrative purposes. You probably wouldn't actually use machine learning to make predictions on data this simple, but again, it's for illustrative purposes here. So next, I'm going to go ahead and run these next few cells. So again, to run a cell, it's Command Enter, and then I'm going to go next, Command Enter, and then Command Enter. Okay, so plot data. So up top here, we're looking at the data with just their raw values. And so this is another way to illustrate the data. So instead of just looking at the raw values, we can actually plot it. So here on the bottom, we've got exam 1 score. And here on the y-axis, we have exam 2 score. And each student is represented as a point. And so the green students represent students who were admitted, or excuse me, the green points represent students who were admitted, and the red points represent students who were denied. So this makes sense. Yeah, we can see that in the upper right quadrant, these students were admitted because they did decently well on both exam 1 and exam 2. I guess one thing that's somewhat interesting to note is that doing well on one exam is not enough. So for example, these students down here did well on exam 1, did very well actually, above a 90, but did very poorly on exam 2, below a 40. So they were not admitted. So it seems like you have to do decently well on both exams to get admitted. Okay, so here's a question for you guys. So just looking at this data, is there any obvious kind of trend or boundary that you could see? Is there an obvious kind of like curve or line or something you could draw to separate the green points from the red points? Got someone in the chat. Okay, someone said decay curve. Yeah, so decay curve, that's a really good point. Like it looks like it could be some like exponential decay or something to separate these two classes. All right, Ryan's saying he fixed it by typing Jupyter Notebook list into terminal, copying the link or copying the URL into my browser. Okay, so yeah, if you're having issues with Jupyter Notebook, feel free to do that. Like I mentioned, I'm gonna post this completed code at the end. So if you're not following right now, that's totally fine. Okay, so decay curve, that's a really good answer. Does anyone have any other suggestions about how you could do it? Maybe how you could quantify it, right? So could you take like a weighted average of these two? Any ideas about how you would do it with numbers rather than just like looking at it? All right, we got some answers. Okay, so someone said slopes. Yeah, so that's a good point. You have to look at, okay, what's the best slope going to be for this line? And Ryan says, okay, fit a linear regression model. Okay, so that's interesting that you say linear regression. So that's a really good answer. We're actually going to do something very similar to linear regression, but in this case, it's not actually going to be linear regression because instead of trying to find the line of best fit, we're going to look for the line of best separation. So that's actually called logistic regression, and I'm going to show that later. So these are all really good answers. And the reason I asked this question was to motivate why machine learning is useful. So if we have a data set this simple, it's pretty easy to look at it and just be like, okay, yeah, we should find some curve here, and that's probably going to be good. But imagine if we had more features. Right here we have exam 1 score, exam 2 score. What if we also had GPA? What if we also had class rank? What if we had all this other information? Then we couldn't visualize it in 2 dimensions, and it would be more difficult to figure out how to separate these two classes. So that's one point. The other point is that machine learning does all this implicitly for you. It'll draw the curve, it'll draw the line, and it'll figure out what the best curve or line to draw is without you having to specify anything other than the data. So that's the reason why machine learning is really useful, and we're going to see that later on. Okay, so next, going to call this, or not call, we're going to define this decision boundary function. So it's very important that you run this cell before proceeding. All right, so thanks for bearing with me through all that. So now we're actually going to get into the machine learning. So we're going to look at a few different algorithms, and we're actually going to be writing the code for them. So this is the part where we're all going to be writing code. Actually need to add stuff rather than just running pre-written cells. So the first classifier we're going to create is called KNearest Neighbors. It's really simple. All it does is use neighboring points to make a prediction for new points. So all these cells are going to look pretty much the same in their structure. First, we're going to import the classifier from a library called sklearn, which stands for scikit-learn, which is like scientific toolkit for machine learning. That's why it has its name. So we're going to import it, create an instance of it, fit it, and then actually make some predictions. So first, I'm just going to say from sklearn dot. Oh, and another thing about Jupyter Notebook, like any IDE, it's got tab autocomplete. But the tab autocomplete is actually really nice when you're working with these packages because you can see what all the sub packages are. So we're going to say from sklearn.neighbors and now import, and now I'm going to hit tab again. And so KNeighbors classifier, this is with a capital K. So I'm going to be using tab autocomplete a lot because it makes things a lot easier. All right, so we're going to import it from sklearn. And now I'm going to go ahead and run the cell. And so I'm going to run it in order to actually see what the arguments to this guy are. So imported it, now I'm going to create an instance of it called KNN. KNN equals KNeighbors classifier, and throw some parentheses on the end. These parentheses are really important. And so now I'm going to go inside the parentheses and hit shift tab. So shift tab is going to show me what all the parameters are here. So it's KNeightors classifier. It turns out that this value K is the number of neighbors, and that's this guy right here. So we can see these are the default parameters. The default number of neighbors is 5. So I'm going to go ahead and copy and paste that in just to be explicit. Doing this won't actually change anything, but it just makes it very explicit what we're doing. So KNeightors classifier, awesome. And again, so hitting shift tab here, that's only going to work if you've run the cell up to this point, or specifically if you've run this line, because this line brings in the KNeightors classifier and allows you to see what it does. So after doing that, I'm going to call knn.fit, and now throw some parentheses around the end, and now capital X, lowercase y. This is really important that you do capital X and lowercase y. And so the reasoning behind that is up top here, when we set up the features and the labels. So features are the things that we use to make predictions, and labels are the things that we're trying to predict. So here X is capital because X is a matrix. It's 2-dimensional. So here we've got 2 exams and we've got a bunch of students, right? And so here Y is lowercase because it's a vector. It's only 1-dimensional. We only have students and 1 admittance category. And so that's pretty standard mathematical notation. And so that's why we do it that way. And so so just want to be explicitly clear about capital X, lowercase y. All right, so after that, we're going to call this decision boundary function, and then we're going to pass in KNN. So this is what the cell should look like. So once we've got that, we can go ahead and run it, and this is where things start to get pretty interesting. Go ahead, run it. Oh, check that out. All right, so this is what the decision boundary function does. So here you can see we've got the original data, these dark green points and these dark red points, and then we've got this pink and light green region. So these regions correspond to what this classifier, KNearest Neighbors, predicts as being denied and admitted respectively. So yeah, so that's KNearest Neighbors. I haven't really explained how it works aside from saying it uses neighboring points to make a prediction. Well, that's pretty self-explanatory, right? That's the name. So how does it actually work, right? So let's say you wanted to make a prediction for a new point right here where my cursor is. So here we have the number of neighbors set to 5. So it looks at the 5 closest neighboring points. So those 5 closest neighboring points are this green guy, these 2 red guys, and these 2 red guys. So it says, okay, 4 out of 5 of those neighboring points are red, so I'm going to predict red. That's all it does. Super simple. All right, so now we can set the number of neighbors equal to 1. So when we change the number of neighbors, this decision boundary right here is going to look different. So when we do that, we can see it looks a little bit different. So now here's a question for you guys. So here we have k nearest neighbors with k equal to 1. What if we set the number of neighbors k up to 25? What's the boundary going to look like? Is it going to look more kind of spiky, or is it going to look more smooth? Any ideas? Okay, someone's saying smooth, someone's saying spiky. Oh, we got 2 votes for spiky. All right, and then 2 votes for smooth. Okay, cool. So all right. So yeah, so we can go ahead and see. So when we run it, we can see it looks a lot more smooth. It almost looks like a straight line. And so why is that, right? Why does that make sense? So the explanation is actually pretty intuitive. Basically, when we have the number of neighbors set to 1, the decision boundary is pretty is spiky because of points right between the 2 classes. For this spike right here, this spike is totally determined by this single point. Whereas when we set the number of neighbors up to 25, that spike no longer exists because you're using a lot more points to draw the boundary. So that's kind of a hand wavy explanation. But the point is, it is pretty intuitive. And when you set the number of neighbors higher, it kind of focuses more on the general trends in the data rather than the specific data points, rather than 1 or 2 data points. So that's k-nearest neighbors. I'm going to set it back to 5. All right, so there it is. Pretty simple, a good start to start talking about machine learning. Next, we're going to talk about logistic regression. So like someone mentioned in the chat earlier, maybe we could use linear regression for this data set. So we're basically going to do that, but again, we're going to draw the line of best separation rather than the line of best fit. Also, these first 2 algorithms aren't like super interesting, but the ones later on, it gets progressively more interesting. So just hang in there. I hope you're having a good time now, but if not, it gets even better. All right, so I'm gonna say from sklearn dot linear model, right? I said we're gonna draw a line. So sklearn dot linear model import, and then I'm gonna say logistic regression. And so these are capital because it's a class. So we're gonna import logistic regression, and now I'm gonna create an instance of it called log reg, and then I'm gonna say logistic regression and throw some parentheses on the end. These parentheses are important because we want to make an instance of this class. So next we're gonna say log underscore reg dot fit capital X lowercase y, and finally decision boundary log reg. So that's what the shell should look like, or excuse me, that's what the cell should look like. From sklearn.linear model import logistic regression log reg equals logistic regression fit and then decision boundary. And again, remember this capital X lowercase y. So I'm going to run it, and we can see that it draws a line. Great, no surprises here, exactly what I said. But now here comes a pretty interesting question, or a question that gets at the heart of machine learning. And that question is, how does it know to draw this line? Right, this line looks pretty good, but why isn't the line like a little bit further down, a little bit further up, like a little higher slope, a little lower slope? You know, how does it know to draw this specific line? So how does the algorithm actually learn from the data? All right, we got a question in the chat. Math. yeah. So that's a really good answer, and that's what I'm going to be talking about just briefly, because this is just an intro workshop. But the overlying concepts are pretty easy to understand. So basically, to draw this line, the algorithm creates a cost function, which tells you how bad the current model is. And then it simply minimizes that cost function with respect to the model parameters. So I'm going to go to this guy right here to show what that means. Okay, so here we've got this error function. So here we're actually doing linear regression just for illustrative purposes. So here a line is parameterized by m and b, by the slope and y-intercept, right? You guys probably learned this like way back in middle school. So y equals mx plus b, and we want to find the m and b which provide the best fit for this data. So to do that, we create this cost or error function, which tells us how bad the model is. It could be anything as simple as like the difference between the predictions and the current points, or in this case, I think it's going to be the difference between the predicted and current points squared. And so that gives you this nice parabola shape. And so to minimize this error function with respect to the parameters, we simply take steps downhill on this error function. And to do that, we use a process called gradient descent. And so with gradient descent, you take the gradient, which is the derivative in a higher dimension, and that points in the direction of steepest increase. So you move in the direction of the negative gradient to go downhill as quickly as possible to move in the direction of steepest decrease. So that's all it really is. You just take the gradient, move in the direction of the negative gradient. So you adjust m and b in the direction of the negative gradient, and then you repeat. And you keep going until you get to a point where the gradient's flat, or where the derivative is basically 0, which means there's no change. And so that point is going to be a min in this situation. And so that's going to optimize and find a really good fit for the line. So that's basically how gradient descent works. In general, machine learning algorithms optimize some sort of cost or error function to maximize how good the model is, or how good of a fit the model is. And so here with logistic regression, we're basically doing the same thing, but again, we're trying to find the line of best separation rather than the line that best matches the points. And so with logistic regression, there are some caveats. It doesn't actually use gradient descent. It uses a modified method, or excuse me, it uses a modified approach of Newton's method, which if you've taken like comp sci or math like 451 or 455, you will have learned about that. So this whole talk about gradient descent, that's a very commonly used method, and that's why I wanted to talk about it, but that's actually not exactly what's used here, but it's the same general idea. Okay, so that's logistic regression. And so we can see that it draws a line, the line looks okay, but maybe the line's not the best thing you could do, right? It seems like someone mentioned like maybe a decaying exponential would be better here. And so that's actually something we're going to look at next. So next we're going to create a support vector machine. So here I think it's going to make the most sense if I just write the code first and then explain it. So first we're going to say from sklearn.svm, and then we're going to say import svc. So this is support vector classifier. So you've probably noticed a pattern with these cells by now. So next I'm going to create an instance of it called svm equals svc, throw some parentheses on it, and then I'm going to run it. So the reason I'm going to run it is to get inside these parentheses and check out, okay, what are the parameters? So here we've got a lot of parameters. I'm going to deal with these two parameters. So first we've got kernel equals poly and degree equals 2. So those are the two parameters I'm going to set here within this SVC. All right, and so like I said, we're going to draw a curve. So maybe this gives you some idea of what these guys mean when we're going to draw a curve. So next I'm going to say svm.fit capital X lowercase y, and finally decision boundary svm. So I'm going to go ahead and run it. So when I run it, we can see we get this really nice curve. Okay, awesome. But I haven't actually explained how SVMs work at all, or what it means to be a support vector machine. So SVMs are actually a lot like logistic regression in the sense that they're a linear model. So that might sound really confusing. It's like it's a linear model, but it draws a curve. How is that possible? How is that not a contradiction? So the interesting thing about SVMs is that they're a linear model, but they're a linear model with respect to some transformation of the data. So here we transform the data with a polynomial function of degree 2. So the model is linear with respect to the transformed data. So this might sound kind of confusing, but you can think about it this way. Earlier, we looked at the equation for a line y equals mx plus b. So imagine if you had a slightly different equation, if you had y equals mx squared plus b. Here, the model is still linear because the m and the b term, those are the same as just y equals mx plus b. But here, when you have y equals mx squared plus b, then the resulting plot is going to be a curve. And so it's pretty much the exact same thing here. We're transforming the data with a polynomial function of degree 2, then drawing a line. And so that line is going to be linear with respect to the transformed data, but it's going to be a curve with respect to the original data. So that's basically how SVMs work. So here's a question for you guys. So if we set the degree equal to 1, what is it going to look like? What is this curve going to look like? Any ideas? Oh, someone answered. Line. Yeah, exactly. Yeah, so let's see. Oh, someone said smooth. Okay, so if we set degree 1, we can see, okay, yeah, it draws a line. And so this is what we're expecting, right? Because when we transform it with degree 1, we're not actually really doing anything different. So here's a somewhat more interesting question, right? So we have degree 2. What if we set it up to degree 3? How is that going to change things? Some said, well, degree 0.5 or -1 work? Well, let's see if it'll work. I haven't actually. Oh, nope, doesn't. Or okay, it's a valid parameter, but it messes things up. Let's see, degree -1. I bet it's gonna yell at me for this. Oh yeah, okay, it does yell at me for this. So 0.5 actually doesn't work very well. Yeah, so let's see. So we did degree 2. So it will create a curve that more closely matches the data with degree 3. Well, let's see. Okay, degree 3. Okay, so this is what degree 2 looks like. Degree 3. Okay, well that's interesting. It looks pretty much the same, right? What if we do degree 4? Okay, also pretty much the same. What if we do degree 5? Okay, still pretty much the same. Degree 6, pretty much the same. So what's going on here? Well, the interesting thing to note with this is that when you increase the degree, it still keeps the lower degree terms. So for example, degree 2 has a degree 1 term, degree 3 has a degree 2 term and a degree 1 term. And so the point is that with degree 2, it's a really good fit for the data. In fact, it's perfect with respect to the classification error, meaning that there's no error here. There's no red in green and there's no green in red. So when you increase the degree, it'll actually set the coefficients for the higher degree terms very close to 0. And so that'll result in very little change for a higher degree because degree 2 fits the model, or excuse me, fits the data very well. So that's something pretty interesting to know. And I guess you could say that the SVM is pretty smart in that respect. All right, so that's about it for SVM. Next, we're going to go ahead and look at a decision tree. So decision trees, these are some of my favorite algorithms. They're pretty intuitive, or it makes a lot of sense in terms of the way a person might make a decision looking at this data. So again, I'm going to write the code first, then explain how it works. So I'm going to say from sklearn.tree, and then I'm going to say import, and so capital D, decision tree classifier. So decision tree classifier, and then I'm going to create an instance of it called tree equals decision tree classifier, throw some parentheses on the end. Next, tree.fit capital X lowercase y. And now finally, decision boundary tree. Okay, so this is what the cell should look like. Give you a second to type that all. All right, so this one's pretty interesting, I'd say. So now we're gonna go ahead and run it. Whoa, check that out. It looks crazy, doesn't it? It looks like a staircase almost, right? Like what's the deal with this? Like up top we had these nice curves, this like pretty straightforward line. But this guy looks all crazy. Like what's going on here? Yeah. So this is the boundary a decision tree draws. Next, I'm gonna run this cell right here. So chances are, unless you have Python GraphViz installed, this cell isn't going to work for you because this package doesn't come with Anaconda. So I would recommend just looking at my screen for now, and then you can install it afterwards. So I'm going to run it, and so we can see actually what the tree looks like. So this is what the tree looks like corresponding to this decision boundary. So decision trees, they're a very inquisitive algorithm, which means they ask a lot of questions about the data. In fact, each vertical or horizontal line here corresponds to a single question that the tree is asking about the data. So for example, let's see, what is a good question? So this guy right here, right? So this line is exam 1 score around, what would you say, maybe like 50, 56, 57? So it asks, okay, is exam 1 score less than or equal to or greater than or equal to 56.7? If it is, then I'm going to ask some follow-up questions. If not, I'm going to ask some follow-up questions, but most likely predict denied, most likely predict accepted for that. And so we can actually see the one-to-one correspondence between the tree down here and the decision boundary up top. So here we can see this is the question that asks that, exam 1 less than or equal to 56.7. And so when we follow the tree down, we can see all the questions it asks and all of the decisions it arrives at. So all of these nodes, except for the leaf nodes, are questions, and all of the leaf nodes or the nodes at the bottom are decisions. For example, this is a decision, it predicts denied. It's a decision, predicts denied, predicts admitted. So that's how the decision tree works. But wait, you might be wondering from the previous algorithms, right? I've told you how they work, but then I've explained actually how they work or how they figure out what line to draw, right? I've said logistic regression draws a line, but how does it know what line to draw? Decision tree, ask questions. How does it know which questions to ask? So that's a very natural question that you should be asking yourself. And so decision trees, okay, how do they know which questions to ask? So they basically do a greedy search of all the possible questions they could ask, and then iteratively keep asking questions. They ask follow-up questions. So what I mean by this is they sort all of the points in ascending order, and then they look at the midpoint between two consecutive points as a question. So for example, if you have like points like 1, 3, 5, it would say, okay, with value 2, it could ask, okay, is it less than or equal to 2? And then it repeats. And so with each of these questions, it looks at a quantity called impurity, which measures basically the amount of green in red and the amount of red in green. So this makes sense why it's called impurity, because it's impure if you have some mix like this, some mix of red and green red. And so it just chooses the first question that, or excuse me, it chooses the question that minimizes the impurity, and then it repeats, and then it asks a follow-up question. So this impurity, it's very similar to up top, like we were talking about the error. Impurity is basically the prediction error with a decision tree. So it just asks the questions that minimize the impurity, and then it repeats, and then it keeps asking questions. Yeah, so that's basically how decision trees work. With this tree, it's just like any tree in computer science. It's got the same properties. It's got a root node. It's got leaf nodes. Each node has a parent and or children. Yeah, and so another thing this tree has is it has depth, which controls how big it is, or specifically it controls how far it is vertically, up and down. which also in turn controls how wide it is horizontally. And so that's actually a parameter here. So if we look at all the, actually I'm going to do this. Yeah, so if you look at all the guides here, so a lot of these correspond with things you might expect in trees, right? Max leaf nodes, min impurity decrease, like I was talking about. And so we've got this max depth, and currently it's set to none. So what it means when it's set to none is that it's going to keep asking questions until it gets the best possible split or the best possible impurity. So here you can see this is perfect, right? There's no green and red, there's no red and green. And that's because the default parameter of max depth is none. So what if we set it to 1? So if we set it to 1, how many questions is it going to ask? How many lines is it going to draw? Any ideas? Max depth equal to 1. All right, so if people aren't sure, then we can just go ahead and try, right? So max depth equal to 1, we can see it asks 1 question. And so we can actually see what the tree is going to look like. So we can see the tree, okay, it just asks 1 question. But here's something that's kind of interesting. The question that it asks is the same when the max depth is 1 as when the max depth is none. So this is the greedy property of the decision tree, is that it doesn't think ahead. There's no backtracking. It just does the best thing at every given point in time and then repeats. So that's what I mean when I say the decision tree is greedy. But going back to the thing about max depth, so when you set max depth equal to 1, it asks 1 question, and we can see what the question is. So for you guys, what if we set the max depth equal to 2? How many questions is it going to ask now? Any ideas? Max depth 2, number of questions? Oh, all right. So someone says 2. Okay, yeah, that makes a lot of sense, right? So max depth 1 question, max depth 2 questions. Let's see. All right, cool. So we could see it. Oh, someone else said 4 questions. That's interesting. Oh, 3, I think. Oh, wow, very clever. Okay, so we got 2, 4, and 3. So we got a good range. We can see how many questions it asks. So it asks 1, 2, 3 questions, right? Remember I said each line corresponds to a question. Someone else in the chat. Root children plus 1 for each of the 2 children. Yeah, exactly. So that's a really good point. So we can see that. And so we can see, yeah, exactly. So the root plus each of the root's 2 children corresponds to a question. And so again, these leaves down here, these correspond to decisions. All right, so it asks 3 questions. And so now we can come up with a formula for the number of questions given the max depth. Or specifically, we can come up with a formula for the upper bound of num questions. Actually, okay, I could just do this down here. Okay, upper bound on the number of questions. So that's going to be 2 to the power of max depth. So that quantity minus 1. Actually, I'll do it like this. Right, and so it makes sense that it's 2 to the power of, because this guy, it's a binary tree. And so it's minus 1 because it counts everything except for these guys. So it's always going to be like 2 to the power 1 plus 2, or excuse me, 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2, so on. But another interesting thing to note is that this max depth is going to be an upper bound, so it won't always ask that many questions. So what's the upper bound going to be for max depth equals 3? Any ideas about that? Max depth equals 3. The number of questions will be all right, 7. Yeah, exactly. Right, because 2 to the power of 3 is 8 minus 1, which gets you 7. Yeah, so that's exactly correct. But then when we actually do it, we can see, okay, how many questions does it actually ask? It asks 1, 2, 3, 4. It only asks 4 questions, even though it could ask up to 7. So what's the deal with that, right? Why is that happening? So if we look at the tree, all right, looking at the tree, okay, we can notice a few things that are pretty interesting. The first thing that jumps out to me is that here, it stops early. It could ask a question here, but it doesn't. This is a leaf node. Instead of asking a question, it makes a decision here. So you might be wondering, okay, why is that? Well, if you look at what's happening here, if you look at this value guy right here, it says 9, 0. So that means that this node is actually pure, or the impurity with this node is 0. So everything here that's red is predicted as red. So it can stop early, and that basically just shows that this max depth is an upper bound. And the same thing is happening here, although these guys are a bit more complicated. So what's happening here is that so it makes a kind of like false split where it creates a split that decreases impurity, but the split doesn't actually do anything. So it goes from an impure node 353 to a node that's pure 045 and a node that's impure. So this is actually considered more pure. So that's a little more complicated. If you don't understand it, that's totally fine. But the point is that this max depth sets an upper bound. So I'm just going to set it to none. All right, cool. And so this last algorithm we're going to talk about is a neural network. So I've only got a few minutes left. I'm going to try to squeeze this in there because this one's kind of fun. So with neural networks, you've probably heard that neural networks are very powerful algorithms. They can be used for everything from computer vision to natural language processing. Yeah, so pretty powerful algorithms. You might have even heard they simulate the way the brain works, which is somewhat true. That's pretty big approximation. But yeah, neural networks. So we've got this very simple data set, and we're going to use a very complicated algorithm to make predictions. So right. Is there going to be a problem? Should there be a problem? Right, it should work fine if it's powerful, right? So let's see what happens. So first, not sure if I should explain it first or write the code first. Sure, I'll explain it first. So first off, so with a neural network, you might have seen a diagram that looks a little bit like this, where you've got some inputs, some hidden layers, and an output. I've got a question here. Will this be recording? Yes, this will be recorded. And I will also post the code, so all good. Okay, yeah, so input, couple hidden layers, and output. So here the input layer corresponds to the original data and the output corresponds to the predictions. And the sizes and shapes of these hidden layers are something that you control as the programmer. So how does a neural network work? Well, each of these nodes is basically like a single logistic regression classifier in the sense that each of these nodes basically draws a line, and then you have some activation function that you pass it through. So basically all of these nodes draw a line, and then you pass it through some function, draw a line, pass it through some function, and then you have the output or the prediction. And so you repeat this process. And so that's what makes neural networks really powerful, is the fact that you have all these nodes where they're each learning some relationship in the data. When you stack them horizontally and vertically, they can make good predictions. All right, so that's that with the neural network. So I'm going to write the code. I'm going to try to squeeze this in there. This might go over just like a couple minutes. If you have some place to be, that's totally fine. So I'm going to say from sklearn dot neural network, I'm going to say import MLP classifier. So MLP classifier, what is this? So MLP stands for multi-layer perceptron, which might sound kind of complicated, but that's basically just each of these guys, each of these neurons is called a perceptron, and we just want multiple layers of them. So multiple layer perceptron, and we're using it for classification. Next, we're going to create an instance of it called NN, and then we're going to say MLP classifier, throw some parentheses around, then I'm going to run it in order to see what the arguments are. So the first argument is hidden layer sizes, which controls how big the network is, or it controls these blue guys in this diagram. I'm going to go back to it, hidden layer sizes, and then I'm going to say 25. So we just want one hidden layer with 25 nodes. This is like somewhat arbitrary. There are rules for how to set this, but I'm just going to set it as 25 for now. Next, I'm going to do nn.fit capital X lowercase y, and finally decision boundary nn. And so once we've got all that, okay, this should be good. So we've learned that neural networks, very powerful classifiers because they can learn complex associations in data sets with their multi-layer structure. Each perceptron is basically like a single logistic regression model. So very powerful, should work pretty well, right? So let's run it. Oh God, this looks terrible. Oh, okay. So we got to figure out how to debug this, right? So is there an issue with the code? Okay, so I'm going to use my favorite debugging strategy, which is to change absolutely nothing and just run it again. So when I do that, right, you guys saw me. I didn't change anything and I ran it again and we get something totally different, but it also looks terrible. And so I could just keep doing this. Oh, okay, this time it's yelling at us. It's telling us something. So it's telling us that, okay, the convergence warning, maximum iterations reached and the optimization hasn't converged yet. So this is interesting. And this actually goes back to how neural networks learn. So it turns out that neural networks actually learn using the same process that we discussed with linear regression here, which is through gradient descent. However, since the structure is much more complicated, since you have multiple nodes, since you have all these parameters, the function is going to look less like a bowl. It's going to be less simple. It's going to be more complex, something like this, right? And so the point is with gradient descent, it tries to go downhill. But let's say you start out over here, you could end up down here. But if you start out up here, you could end up at a totally different point. So gradient descent, where you end is determined by where you start, and where you start is actually randomly initialized. So in this example, these parameters m and b are randomly initialized because going into the problem, you don't know what the line of best fit will be. So that explanation was kind of quick, might be kind of complicated. No worries if you're not following it. But basically, this warning is saying that we haven't taken enough steps in gradient descent, or here we haven't taken enough steps downhill. And so that makes sense for a function like this. If you haven't taken enough steps downhill, you might not get to a point that's flat. So if we bump that up, if we bump up the max iter, yeah, is that here? Okay, let's see. Let's see what it's called. So here we've got max iter, it's set to 200. So let's bump that way up. Let's bump it up to like 1,000 or 10,000, and let's see what happens. So if we do that, okay, well, it still looks terrible, but we got rid of the warning. So if we keep doing that, okay, still looks terrible. Oh, see, it took longer then, but it worked. So this is looking pretty nice. So that this whole thing with neural networks might have been really confusing. It's like, what is going on? So the point that I'm trying to or the big takeaway that I'm trying to give you guys is that using a complicated model isn't always good when a simple model can do the trick. In fact, using a complicated model might even backfire in some pretty significant ways. So that's basically the takeaway with this. If you didn't understand the stuff about gradient descent or all the parameters or structure, whatever, that's totally fine. The point is you shouldn't use a complicated model when a simple model can do the job because of behavior like this. Yeah, and it's also fun just to like mess around with it and see the different things it draws. All right, so I'm gonna leave it at that because this one looks pretty good. All right, so that's about it for the workshop. I'm gonna post this code on the same place that you cloned the repo from, and the recording I think is gonna be up on YouTube. Catherine, you can correct me if I'm wrong about that. Yeah, so that's about it. Thank you guys so much for attending. If you have any feedback, I would really appreciate that too. But otherwise, enjoy the rest of Hack PSU, and yeah, have a good day. Thank you all. Got something in the Q&A. That's pretty much so far. Oh, thanks guys. I appreciate it. Feel free to close the webinar when you. Oh, okay. All right, yeah, if you guys have any other questions, I'll be here for, I guess, a couple more minutes. Do you know anything about multi-object evolutionary algorithms? Honestly, not really. Evolutionary algorithms, yeah, that's a pretty cool topic. But unfortunately, I'm not too knowledgeable about it. Oh, can I have the repo link? Yeah, sure. One sec. Panelists and attendees. Okay. Yes, that's the repo link. All right, yeah. So if there are no more questions, I'll go ahead and close the webinar. I apologize if you guys had issues with Jupyter Notebook. I think yeah, Ryan had the solution where he did Jupyter Notebook list on the terminal. That worked. So I'm gonna post this code immediately after on the same the same repo link, and the recording should be on YouTube, I think. Okay, so once again, thank you guys. Gonna head out now. Have a great rest of your day. All right.